Today we are going to learn Poynting theorem. To assemble a static charge distribution. So that work against the electrostatic repulsion that is given by epsilon naught upon 2 integration square of electric field d tau, the volume element. Similarly, in order to flow the current, we need to do work against the back EMF, magnetic work, you can say 1 upon twice mu 0 integration b square d tau. Now this suggests total energy stored in electromagnetic field that is given by, let's say we denote it by U electromagnetic, which is equal to 1 by 2 integration of epsilon 0 e square plus 1 upon mu 0 b square d2. Suppose if we have some charge and current configuration at time t and electric field and magnetic field, in the next instant dt the charge move around a bit. So what the question is, how much the work dw is done when the electromagnetic forces are acting on these charges in the interval dt. So according to Lorentz force dot dl, which is equal to q into E plus V cross B, where V is the velocity, B is the magnetic field, and dotted with the displacement. So displacement will be given by velocity into small time tt. So that will be equal to QE dot V dt. So the term V cross B dotted with V dt, this will be equal to 0 because there is a cross product between the V bar and V bar. So del cross B, that will be a perpendicular vector to V, and V perpendicular to V. So this vector dotted with the V, that will give me cos of 90. So cos of 90 is 0. That's why we will get it is equal to 0. Now we know that the charge distribution, so total charge enclosed in that system, that is given by the volume charge density into d tau, and rho v will be equal to j. So how is this? So first of all, what is rho? Volume charge density. So rho is charge upon volume into v is the velocity, so that is meter per second, let's say. So this will be equal to q, that is charge, into length divided by meter square into meter into second. So this will give us, this will give us meter will get cancelled, so we will get q upon meter square second. So q upon meter surface current density. So this is your surface current density. Here charge upon time, this is your current per meter square, that is your surface current density. Now if we take the rate at which work is done on all the charges in the volume V, so that dw per upon dt, that is given by E dot J is the electric field, J is the current density, surface current density, d tau over the volume, let's say V. So here E dot D is the work done per unit time per unit volume. which is to say the power delivered per unit volume. We can express this quantity in terms of fields alone using Maxwell's law by eliminate Maxwell's law to eliminate J. So here E dot J, that is equal to 1 upon mu 0 E dot del cross B. Okay, E dot del cross B minus epsilon 0 electric field dot delta E upon delta T. So now we have product rule. So product rule, by using the product rule, we have del dot A cross B, that will be equal to B dot del cross E minus E dot del cross B. So we invoke the Faraday's law, so which says that del cross E is equal to minus delta B upon delta T. So it follows that E dot del cross B, so which is equal to minus B delta B upon delta T minus del dot E cross B. Now meanwhile we have B dot delta B upon delta T, which is equal to 1 by 2 delta by delta T of B square, magnetic field square, and E dot delta E upon delta T, so that is equal to 1 by 2 delta by delta T of E square. Now so we have E dot J equal to minus 1 by 2 delta by delta T. We will take it out and we will take the E0 epsilon 0 upon E into E square plus 1 upon mu 0 into B square, magnetic field square. So minus 1 upon mu 0, the second term, del dot E cross B. So if we put this equation in the equation number 8.6 and apply the divergence theorem to the second term, so we get dw upon dt, that is equal to minus d by dt. So in bracket over the volume V, 1 by 2 epsilon 0 E square plus 1 upon mu 0 B square d2, and the second term will be 1 upon mu 0. By divergence theorem, this volume integral will change into the surface integral, and we have A cross B as it is, dotted with the surface element dA. So if we use this to equation, finally what we get is, this is your final equation. Now where S is the surface bounding volume V, so this is the integral form of the Poynting theorem. It is the work energy theorem of the electrodynamics, the first integral on the right hand side of the total energy stored. So first integral part, so this gives us the total energy stored in a electromagnetic fields, and the second term evidently represents the rate at which the energy is carried out of the volume V across the boundary surface by the electromagnetic fields. So this is the second term. So Poynting theorem says the work done on the charges by electromagnetic force is equal to the decrease in the energy stored in the field less the energy that flowed out through the surface. The energy per unit time per unit area transported by the fields is called as Poynting vector, and this Poynting vector, it is given by 1 upon mu 0 E cross B. Okay, and significantly S dot dA. So this Poynting vector dotted with the area element, this gives us the energy per unit time crossing the infinitesimal small area dA. The energy, that is the energy flux. If you like to so S is the energy flux density. So we will see many applications of Poynting theorem related to electromagnetic waves in power transmission of waveguides, radiation from antennas, optical fiber, energy transfer, electromagnetic wave propagation. So like this way there are many applications. We can write the Poynting theorem more compactly like this. So dw upon dt, so that is equal to minus d of electromagnetic waves, energy of the electromagnetic wave stored in a energy stored in the electromagnetic wave, minus so surface integral over s dot. So this is the compact form of the Poynting theorem. So of course the work done on the charges will increase their mathematical energy, that is kinetic, potential, or whatever. If we let the mechanical energy, U mechanical denote the mechanical energy density, so we have so that dw will be equal to d by dt of, so dw upon dt, that will be equal to d by dt of over the volume V, U mechanical over d2. So then we have d by dt of over the volume V, U mechanical plus U electromagnetic. So this will give me minus del dot S. So this is the differential version of the Poynting theorem. Compare it with the continuity equation expressing the conservation of charge. So del bar rho upon del bar T, which is equal to minus del dot J. So the charge density is replaced by the energy density, mechanical plus electromagnetic, and the current density is replaced by the Poynting vector. The latter represents the flow of energy is in exactly the same way that the J describes the flow of charge. So thank you.